The XB-70 Valkyrie was developed during the Cold War as a strategic bomber designed to travel at Mach 3 and deliver nuclear weapons from high altitude. At the time, the US believed that speed and altitude were the best protection against enemy defenses. The goal was to build a long-range aircraft fast enough to reach its target before it could be intercepted. The aircraft was designed to cruise above 70,000 feet, a height where enemy fighters could not easily reach it and where missiles were still limited in capability. Its speed would reduce the time spent in hostile airspace, making interception extremely difficult. The Valkyrie was meant to deter nuclear conflict by assuring the ability to strike back if attacked. Reaching these speeds required unusual engineering solutions. The aircraft's exterior was made from stainless steel honeycomb panels that could withstand extreme heat caused by friction at Mach 3. At such speed, air resistance heats the aircraft's structure, which would damage normal materials. The Valkyrie's metal design solved this problem and allowed sustained high-speed flight. Its wing design provided additional efficiency. The outer sections of the delta wings could fold downward at high speed. This technique created a compression lift effect by trapping shock waves under the wing, increasing aerodynamic efficiency. Instead of fighting against air resistance, the XB-70 used supersonic airflow to maintain stability and lift at high speed. The XB-70 was powered by 6 General Electric YJ93 engines. These engines required a special fuel developed to handle extreme temperatures produced during prolonged Mach 3 flight. With more than 30,000 pounds of thrust per engine, they allowed the aircraft to accelerate quickly and maintain high speed for long distances. Without these engines, the Valkyrie's performance goals would not have been possible. However, the strategic environment changed before the aircraft could enter service. Advances in Soviet surface-to-air missile systems reduced the advantage of high-altitude flight. Missiles could now reach the same airspace the Valkyrie relied on for safety. No matter how fast the bomber was, it could not fully guarantee protection against modern missile systems being developed. The rise of intercontinental ballistic missiles also impacted the program. ICBMs could deliver nuclear warheads faster with no risk to pilots and at a lower cost than building large fleets of bombers. As missile technology improved, strategic planning shifted away from high-speed bombers. The Valkyrie's mission became less relevant and funding was reduced. Instead of being deployed as a bomber, the XB-70 was reassigned as a research aircraft. It was used to study the behavior of materials, engines, and aerodynamics at sustained high speeds. The data collected helped advance aerospace technology and contributed to later research in high-speed flight. Its value shifted from defense to scientific development. In 1966, one of the 2 XB-70s was destroyed during a formation flight for a photoshoot when a smaller aircraft collided with its wing. The crash resulted in the loss of the aircraft and the death of a pilot. With only 1 Valkyrie remaining, the research program continued, but on a reduced scale. The surviving aircraft was used mainly for sonic boom and aerodynamic studies. The final flights of the remaining XB-70 focused on testing airflow, aircraft heating, and shockwave effects at high altitude. This research contributed to future designs, such as the SR-71 and various supersonic aircraft concepts. Though it was never used operationally, its test results played a significant role in advancing aerospace engineering. Today, the only remaining XB-70 is displayed at the National Museum of the US Air Force. Its size, shape, and construction reflect engineering priorities of its time: speed, altitude, and endurance. It represents a period when strategic planning favored aircraft designed to outrun threats rather than avoid them through stealth or missile defense. The Valkyrie project shows how technology can become outdated even before it is used. Although it did not enter active service, it remains a valuable example of how changing military needs can redirect innovation. Its engineering solutions continued to influence later research long after its original mission was cancelled. The aircraft remains significant because it expanded the limits of what engineers thought was possible in high-speed flight. From materials to aerodynamics to engine technology, it contributed knowledge applied to later projects. The XB-70's legacy is practical. It helped build the foundation for future designs rather than serving as a weapon.